We're going to talk to you about making handheld surface measurements fast and precise, really designed on the shop floor. And thanks again to Flavio for arranging everything. He's our local representative and the guy who can help you out with any further questions or arranging demonstration or parts measurements, after the webinar is over. So surface measurements can mean many things to different people. They can be roughness, waviness, or shape, depending on what someone is interested in. Other people, when they talk about surface measurements, are thinking about geometries, and small geometries like radii and chamfers can be extremely important. Or they might be talking about defect measurements, so scratches, pits, spalling, gouges, things like that. And so for this particular presentation and the product we're going to be introducing you to, we're going to be talking mostly about waviness or small microgeometries, chamfers and radius, and defect measurement as well. And so I have a few slides here, and then we'll get into real live measurements with Kramer. And again, thank everyone for attending. So a little bit of background here, why shop floor 3D measurements? And that's really because micro scale defects matter a lot. They can affect performance via efficiency. They can cause leaking. They can cause damage to other parts or even injury to people. So if an edge break on a machine part is not bigger than 250 micrometers, it can actually cause people to get cut, leading to workplace injuries. And edge break can also affect things like fluid flow. Microscale features also affect longevity. So, too many defects can lead to excessive wear on a part, particularly with things like bearings, gears, turbine blades in high pressure environments. Imperfections in a surface can initiate corrosion, and structural integrity, or the overall strength of a part, can be affected by voids or other defects. And lastly, chamfers and edge radii are designed to prevent cracking. So if they're not of a long enough radius, you can have damage to components in high impact environments. And last but not least, it can affect perception. So the human eye is very good at seeing very small defects, but terrible at estimating their size. And so oftentimes customer will reject parts based on what they see. And if there's not a quantified record of what the defect actually was, you may be stuck actually rejecting a part that's potentially worth tens of thousands or even hundreds of thousands of dollars. I've heard from the aviation industry that certain bladed disc or blisks have been rejected for cosmetic scratches, and actually the InSpec has allowed customers to save literally millions of dollars by saying, no, we measured that. It was actually underneath 2 micrometers deep, so you don't need to worry. So, the moral of the story here is, I guess, good metrology can save a lot of time and a lot of money. So Quality Digest shows that large companies can spend more than $2 million a year due to poor quality control on components they manufacture. And the National Institute of Standards here in the US has showed that the average benefit of metrology investment is 47 to 1. So every $1 you spend on appropriate metrology, you can save $47 in lack of having to correct issues or failures. And those costs can be internal costs that are within your company, so waste and scrap, rework, things that are very directly measurable, or those costs can actually be external. So what happens outside of the factory? So you have repair costs, warranty claims with customers, meetings addressing customer complaints, travel to go out and visit customers or get parts back, There's throughput issues within the factory and downtime because of that. And then overall customer dissatisfaction and negative perception can really be impactful to a business. And traditional shop floor measurements just aren't sufficient for measuring fine scaled surfaces. So a lot of people still use their eyes or their fingernails or scribe gauges to try and assess depth of a given issue, or they'll use hard gauges for edge break radius. The problem is those are all operator dependent. They're not gauge capable measurements. One operator to the next will get a different result. And even if you go to something like using Replicast combined with an optical comparator or shadow graph or surface profiler, you have high material costs, still a long measurement time, but worse yet, you're still operator and material dependent. So was it the right Replicast? Did it get all the way into the defect? Did the operator cross-section the part at the deepest point? And any uncertainty is going to lead to rejection or reworking, and that's expensive. So quick quiz for folks who've joined us. So visual inspection. So these are 6 identical images on a part of different defects with a bright field microscope. And which pit is shallowest of all these? And it's not really obvious based on just visual inspection. And in fact, one of the biggest, darkest pits of all of them is the shallowest at only 5 micrometers deep. And one of the smallest pits in the upper center of the image laterally is actually the deepest, or one of the deepest, at 80 micrometers deep. So you can't trust your eyes. Equally, you can't trust two-dimensional traces for three-dimensional defects because you simply don't know, are you at the deepest part of the pit? Are you at the deepest part of the scratch? And so here, just moving the cursor by a few micrometers can actually cause a 30% difference in results. So what we need are three-dimensional results. So if you look at the entire pit, you can analyze, as you see in the upper right, that blue region, look at all those points at once, determine the depth that way, and you get an accurate depth gauge that's operator independent. And so along those lines, that's why 4D Technology developed the 4D InSpec and its big brother, the XL. It's really designed to meet the needs of precision inspection. So the two products, and Kramer's going to show you a lot about them, but one has an 8 by 8 millimeter field of view, and you see that on the left. The other has a 15 by 15 millimeter field of view. The resolution of each is just a few micrometers, and the vertical range is 2.5 millimeters for the InSpec and up to 9 millimeters for the XL. They also have long standoff distances, and that allows us to use fold mirrors to look sideways or into pipes or into fillets for tight spaces. And you have a lot of different measurement options, outputs available. So anything from a 4D file that we can use to help you analyze the data better to an XYZ point cloud that you can use for CAD comparison, and Kramer will show you that. There's different configurations, so you can mount it, as you see in the right, on a little mobile cart, and that's pictured in detail on the left here. But here's someone measuring a big cowling on the shop floor. So you can roll the system around. It has its own power supply. That's really the most common configuration among our users, and it gives you hours of battery-free, or plug-free operation, and a very convenient package that goes right to the part being inspected. For even additional mobility, we have a backpack kit, and that allows actually a fully mobile unit. It even has a holster to hold the InSpec. The backpack holds all the power supply, cables, accessories, and then we have a ruggedized Surface Pro from Microsoft so that you can bring the measurements wherever you need, on wing or in tight spaces or inside of a ship, anywhere that it might not be convenient even to have a roller cart. And then people measure almost any type of surface with these systems. We have several hundred fielded in the world. They are measuring anything from carbon fiber, fiberglass, and composites, any metal, plastics, rubber. And then, I'm not going to go through the whole list of part types, but anything from propellers and gears to shafts and weld joints. And then you can do corrosion depth measurements, weld height measurements, and width and volume. You can look at rivets and fasteners, edge break radius, pitting, die peening and laser marking, different geometries, all sorts of different things can be measured with these instruments, and not in a metrology lab, but holding it in your hand, bringing it to the part. And the net effect of that is, again, I won't go through all the details here, but you can save parts, so you have less rework and less rejection. You can significantly reduce measurement time by making an instant result right there at the part. Yields have gone up consistently. A lot of folks worry that adding metrology will lead to decreased yield. But the reality is, an inspector who doesn't have confidence in his result is going to reject parts that are good rather than risking a bad part getting through. So uniformly, people that use handheld 3D metrology see increased factory yield and then also reduce labor. So that can be significant, such that you're doing in situ measurements, or it can be, hours, just by making measurements that used to take a half hour each, just a few seconds. And with that, I'm going to turn the presentation over to Kramer, who's going to show you real live measurements. And again, along the way, please type questions into chat or into the questions box, and we'll answer them. So thanks.
All right, so here's my setup here. This is the 4D InSpec right here. Thanks again for tuning in to the webcast. My name is Kramer Lindell. I'm an applications engineer, and I'll be taking you through what exactly this device is and showing you how to take measurements on different parts, different materials, and different kinds of inspection that we do with this. This does a lot of different things, and we got a lot of different questions about what it can do. So we'll take you guys through as many different things as we can, and feel free to jump in with questions at any time and any requests that you would like to see me take measurements on. So I'll start first with basically what this is. This is a handheld inspection gauge that allows you to take a 3D metrology to the part on a shop floor. And it's right now I have it a handheld mode with a focus aid. So this focus aid allows me to set this device down and be at the right focal distance to be able to be in focus and take this, press this button to take a measurement. So I can put this down anywhere, be in focus, and take a measurement on any defect that I see on a part. So what this is doing is sending an LED that's been polarized in a special way with our patented technology. It's coming down some lenses, reflecting off this surface. You can see the reflection there, and coming back to the camera. Anything this reflects off of back to the camera, we can create a 3D surface map of the surface. So I can set this down on any surface, take this measurement by clicking this button, and pretty instantaneously, we can get a 3D surface map of whatever we're looking at, whether it's metal, like shiny metal, like what we're seeing here, or rubber, carbon fiber, 3D printed objects, wood, anything we want to look at. So I'll start with a quick measurements on the shiny piece of metal right here. It has some marks on it that we can take a look at. So I'm going to measure this. I'm just going to set this down with this focus aid right here, and I'm going to click this button right here, and that will allow me to take a measurement. So I'll switch over to my 4D software right here. I'll go and get rid of all the old stuff here. Go to my live video and give it my crop. And I'll go ahead and get into focus. Real quick. A little bit. All right, there we go. Software's up and running. All right, so this is what my live video is seeing right here. This is my live video from my camera. So what I'm seeing right now. So when it's gray, that means I'm out of focus. If I wasn't really out of focus, you can see it there. I'm out of focus. I can get into focus. And when I'm in focus, it turns green. And green means go. I'll go and take a measurement by clicking that button, like I showed you guys earlier. And I can take a good measurement. So I'm green. That means I'm in focus. I can take a good measurement here. I'll go and put this into feature analysis and look at pit depths here. So anything deeper than 15 microns is our specification we have set just arbitrarily right here. So each one of these features that is deeper than 15 microns, which all of these marks are, they're being flagged as features. And this feature analysis page will tell you everything you need to know about each one of these marks. So it's analyzing every one of these marks simultaneously. And each one of these individual marks has its own set of individual stats. So we're looking at its height here. So it's in depth in this case. Its area, its volume, its width, length, everything we want to know about this particular feature, you can get the information right here. If I want to know how deep this one is, I can go ahead and click this button and it tells you how deep that is. If I know which one's deepest, I'll go and click this, and this one right here is our deepest mark on this in this whole field of view. So as Eric was saying, this is one of the benefits of our 3D analysis. So instead of 2D, where you're guessing where the deepest part of each one of these marks is, it's telling you automatically what the deepest part is of the whole feature. And not only that, it's identifying all of these features simultaneously. So instead of using a 2D trace across each one of these individually, we are analyzing all of these at the same exact time. So that's our feature analysis page. That's one way to view a measurements. We have different options to look at a measurement. We have a contour page, tells you some
Kramer,
roughness. Yeah.
if I may interrupt you,
Yes.
before you get into the features, there is sort of a basic question, which is how well does the system measure? What's the resolution?
Yeah, so as Eric was saying, we have I'll show you the specification sheet again. The resolution is about 2.5 microns. So anything above that, we will be able to measure. Any pit or defect deeper than 2.5 microns, we'll be able to accurately measure. So these right here are much deeper than that, and we can measure that okay and just fine. And with the big brother, it's a little higher at 5 microns, but you have a much wider field of view and depth range, depth range. Sorry. And I can show you what that this system looks like right here. This is the
And
XL version. Yeah.
Sorry, real quick along those lines. They also asked about how we calibrate deep measurements, and Kramer can show you the calibration standard. But we do actually, this is one of the few systems we use 4 different heights, ranging from 100 to 900 micrometers deep in order to calibrate the instrument. So we know not just the accuracy, but the linearity of the system over its range. And calibration is super simple, and Kramer will show you that right here.
Yeah, calibration is a fairly quick process, and it just involves taking a measurement of this tiny little calibration standard. It has a few ridges on it that you'll see a little clearer when you take a measurement of it. I'll go ahead and set that underneath the InSpec and go back to my 4D software here. Go back to my live video. So this is the standard right here. I'll get that lined up. All right, so I can take a measurement of this standard just to show you what it looks like. And I can go to the calibration page. We'll see if I was lined up here. So I'll move it over a little bit, line up these ridges to the overlay here, take a measurement. And the calibration is verified, and that's the calibration process. It's really quick. I can up the significant figures here real fast to show you what we're measuring. But it's a quick process. Calibration is verified. This is the certified height of the standard I'm using, and this is what we are measuring. And the most, it's the percent error we are getting. So we were off by 0.05% on the valleys on average. The most we were ever off on any of these 4 ridges was a 0.09%. So that's how we test our accuracy for depth, and it's a quick measurement.
Kramer, you breezed through that really fast. I'm chuckling how easy it was. So you
Yeah,
put
sorry,
the
I've done
calibration,
it a few times.
you put the calibration standard under the instrument, and then
Yes,
switching over to the calibration view, there are red lines that tell you where
yes,
to line up the ridges. And once it's aligned, you just take a measurement and it tells you whether you're in calibration or not.
exactly. Yeah, so I can run through that real quick again. So I set this calibration standard underneath the InSpec like that. I got it into focus just by moving on the microscope stand. You can move up and down with a knob right here, and that allows you to get actually moving up and down, in and out of focus like that. I'll get it green like so. I can come onto this side right here and open up the calibration screen, and I'll just move this calibration standard to get that red overlay aligned. You can see the ridges there. So I'll align it to those ridges like that. And then I can just take a measurement once I'm all lined up and in focus. So once everything is green like this, once the ridges are lined up to this red overlay, I can take a measurement. It's gonna say calibration verified as long as I'm my system's looking good, and it's gonna tell me what I measured and the certified height. So that's essentially how easy it is to calibrate the system, or to make sure the calibration is still within the specifications. This is what the 3D surface map of that calibration standard looks like, in case you wanted to take a look at what a 3D surface map looks like with the InSpec. You can play with it here. So it's a fairly simple process, and it can be done, in less than a minute. So there's a few ways to view this measurement. We've gone through the feature analysis already. You can view it in the contour plot. This is a good measurement to look at this on. The red is high and the blue is low. This is a deep valley right here, and these are ridges that are higher. And it's giving you some surface parameters and some other measurement data right here. We can look at the measurements in a traces view. So if I want to do a horizontal trace across this standard, I could say how deep is this valley right here, and I can highlight this from this point to this point, and it'll give me a delta Z for how high this this point is right here. And I can also, if I want to know how wide this valley is, I can highlight where it begins and where it ends, and give me about 1,500 microns across from where this begins and where this ends. So there's different ways to view the measurements. Of course, we saw this 3D measurement already. So different ways you can view measurements, and for different applications, each one comes in handy. So the calibration process is fairly easy, fairly quick, and you get the hang of it pretty quick. As you can see, I did it too quickly because I've done it a few times, and you can move along to a different type of defect inspection than what we were looking at earlier. So I can look at a curved sample here. So I have a curved blade and I have a defect circled on this blade. So I can go ahead and still measure this defect and remove with the software the curvature of the blade itself. So I can help this defect stand out amongst the curvature of the blade by removing that curvature. So kind of same idea as measuring this flat surface. I'm still going to use my my focus aid here. And this focus aid, if I want to take out of the stand and use it as a handheld instrument, I can put this focus aid in the front like this, get to an appropriate length, and use this to get to the appropriate length and take a measurement of this defect. So I just set it down once I'm at the right length, and I can take a measurement anywhere I want to. So I have this already circled. I want to take a measurement of this. Once I'm in focus, I'll go ahead and click this button and take a measurement and get a 3D surface map of this surface right here. So I'll go ahead and go back to my software right here. I'll go ahead and first take a measurement with just tilt removal, and then we'll go ahead and remove that shape afterwards. So go into focus, about right there, looks good. So when I'm green, I'm in focus. I'll go ahead and take a measurement now. So this is going to have some curvature to it, as you can see. The blade bending right there. It's kind of drowning out our defect. I'll go ahead and remove that curvature using this variable shape removal right here, and recalculate this measurement. So I can recalculate a measurement I've already taken with different parameters set. So this recalculation will add in the variable shape removal, flattening out this measurement and helping this defect stand out. So there we go, it's flattened out, and there's my defect. Now I can throw this into feature analysis, and I can have this defect be pointed out right here, and that's tell me how deep this is right there, about almost 40 microns deep. And if I had not, yes sir.
This is a nice feature. I noticed there's some high material by that gouge too. Can you maybe lower the peak height and show folks that we can measure both at once?
Yeah, so this is a good example for how these specifications can be moved around, sorry. So right now I have this set at 100 microns just arbitrarily. So if I want to set this at 15 as well, we can see if we are getting these raised materials right here. So you can see
yeah, so the purple.
Yeah, the purple right here. Right here. So these two are raised material next to the scratch. So the scratch causes the material to get raised up next to it, and it's being shown right here and right here. So we're looking for both depths and heights at the same time.
Great, thanks.
Yep. And if we had not removed that, the shape of the parts, it would pick up the shape itself as a defect and drown out the defect itself. So that shape removal is a pretty powerful tool for identifying defects. Now I can take some measurements on other materials. We've been taking measurements on metals, and just for example, I can take a measurement on this little 3D printed part we have here, just as an example of what we can do. Go and take a measurement on this 3D print right here. Get into focus. When I'm in focus, I'm green. Go take a measurement of that. You can see the layering of the 3D print here. So I can draw a trace across whatever I want to look at. Say I was interested in this layering right here. I want to know how deep this surface went. Pull this up. I can see how deep this is. So this delta Z is about 200 microns from here to here in this layering. right here. And we can also look at carbon fiber. I'll take a quick measurement just for.
And even with all these materials with the auto brightness, so you're never having to adjust brightness, even though you're going from black to silver and shiny to not shiny, right?
Yeah, exactly. So I'm not even touching the brightness right now. It's doing the work for me. So I can go from dark to shiny. So I have this auto brightness selected here. So I'm back to this really bright part. It starts out really red, and now this automatically adjusts to the correct brightness. So I took this off and just adjusted it myself. It's getting really bright and overexposed. I can click this auto brightness. It gets down to the correct brightness. Now I can switch back to this carbon fiber. It brightens it up a little bit for me, and it gets the appropriate brightness. So it makes it really easy. Don't have to worry about the adjusting exposure time or gain. It'll do it for you. Now I have this measurement of this carbon fiber. You can look at it here. So the fibers within it. That's pretty interesting, and we aren't too limited by any material we want to measure. All right, and also in defect inspection, we have different attachments to the front end of this. Right now, I'm using a kind of universal focus aid that lets me put it down, measure, put down, measure, and I'll always be at the right focal distance. If I want to take a measurement on of a defect on a blade edge, we see here, I can switch out to a different type of focus aid. So I can use this V groove, if you can see that. And that allows me to ride along this edge and be at the perfect focal distance while riding along this edge. So I'll go ahead and attach that to the front end of this. It just slides in this hole, and I can adjust it so I'm at the perfect focal length, and I can just move this InSpec across here, and I don't have to worry about adjusting for focus either. So I can go to my live video here. I'll adjust focus, get that edge in focus, like so. All right. Okay. So there's my defect on this edge, and I'll go and take a measurement of that. And I will recalculate this with an area of interest and a different shape removal. I'll use a tilt here. So I can go to my measured. This is I can go to previous measurements and recalculate. I'll recalculate this with a cropped area of interest. So I can crop measurements. I like this area right here. Recalculate that surface. Take a look at this. I'll go ahead and lower this a little bit. Give me that data I like, and I can go to traces. I'll use a vertical trace. Now I can see just how deep or wide this is. So if I want to highlight this specific defect, if I say this is the end, right about here, be about 600 microns wide at this specific area, this trace, and I can see that the peak to valley being shown down here is about 530 microns. So this is how I would do a defect analysis along a blade edge right there, using this this tool on the edge of my InSpec here. Another option we have for an attachment that comes with the InSpec is this fold mirror right here, and this goes into the end of the InSpec just like the other ones, and put it like that. This bends the beam at a 90-degree angle. So you can see on the table there. And this allows me to get into tight places and take measurements, whether it be between these fan blades or in a tube or aerospace part. I can show you that right here. So I can get into this part right here that I have in the shop. So the advantage of the 40 InSpec standard is that I can get into tight places. So I can use this fold mirror to get inside and take measurements at a 90-degree angle. So now I can measure the wall of this large aerospace part. I can measure the wall at a 90-degree angle. So I can get all the way into this, take a measurement. I'll go ahead and show you what that looks like. Go back to the software here. I'll go ahead and get this at the right focal distance, that right there. Go to my live video and find some raised material I know that is here. So take a measurement of this stuff right here on the edge of that. And I can go ahead and crop an area of interest. Say I was interested in this specific spot. I can recalculate on this area of interest. I could throw this into feature analysis, analyze how high this raised material is. That's the feature analysis. If I was just focusing on height, I can say that this right here, this raised material, about 200 microns high, right there. And for each of these, it's giving me a report on each one of these features down here. So,
And they're all sorted from tallest to lowest.
Yeah, right now I'm sorting by tallest to lowest, and this one's the highest at 200 microns. And if I want to save this chart, I can save that as a CSV file. If I want to put an Excel or anything like that, I can save this entire window as a screenshot by clicking this button, the screenshot right there, save anywhere I want to on the computer. And I can save measurements as a whole as a .40 file, which would allow me to put that back into the 40 software and invite it I would here with different croppings or different shape removals, different settings in general. I can also save it as a XYZ point cloud, .opd file, or a CSV file if I wanted to export it out to a different software or for any reason. So there's a few different ways to save your findings and all the data that you have acquired with the InSpec. So that covers a lot of our defect inspection on different parts and different materials. We can look at some edge break measurements that I know some people have asked about. So to do that, do some edge break measurements, we can look at our calibration standard. I'll go ahead and bring this camera back around. All right. And this is our edge break standard right here. I'll give you a little clearer view in our PowerPoint, but it has some chamfers on this side and some rounded edges on this other side. And for a little clearer picture, I'll pull this up right here. And you can see on this side we have a chamfer, which is a flat edge machined into a corner that creates 2 45-degree angles in this case, instead of that 90-degree angle right here. This is a way to break an edge so it's not so sharp. And on the other side here, we have a rounded edge. So this edge has been rounded off, so that sharp edge is now a duller rounded edge. And in here we have internal rounded edges, and here we're taking a measurement on this chamfer. So we are perpendicular to the chamfer. That allows us to get data from all three of these planes, this chamfer face, this right plane, and this left plane right here, from the view of the InSpec, that is. So we get data on that, and we can put that into the software analysis and it can analyze the chamfer for us. And same goes for the rounded edges here and here. So we're gonna take some chamfer measurements. First, I'll show you how I would do that right now. Go ahead and get out of this. All right, so here's my standard that we were looking at just now. A chamfer on this face. So to measure that, I will just use my focal aid and bring it up to the appropriate focus point. And I can go ahead and take this measurement, get this stuff out of the way for you guys. I can take this measurement by just clicking this button like I have been doing when I'm in focus. I can take a measurement of this chamfer, so I can get in focus. Switch back to my view here. All right. So here's my chamfer. I'll get that green. All right.
Hey, Kramer, this view always strikes me because you are showing the green in focus, but the area to the left and right are black, at least to the viewer. But we're still
Yes.
picking up data there.
Yeah, so on this left side, you can see I was able to get data. Even though it looks dark to our eye, the InSpec is still getting that data. It's just not as bright as this part perpendicular to the camera is. It just looks dark to our eye, but we are still getting data on all three of these planes. So I'm throwing this into the chamfer analysis software right now. And what this is doing is identifying all the parts, all the data points that belong to the plane, all data points that belong to this chamfer face, and all data points that belong to this right plane. And these data points are shown right here. Say the blue, the red, and the pink, the left chamfer face and the right, respectively. And this 3D data allows us to not worry too much about alignment. You can see my InSpec was tilted slightly. This top was closer to the InSpec than this bottom was. You can see that with the coloring. So I was really kind of like that. Even though it's a few degrees off, it doesn't matter. Like a 2D alignment or a 2D measurement would matter. That would matter a lot. That those few degrees. With a 3D measurement, we can remove that tilt and get accurate data. So we're displaying our chamfer results down here. We're getting that chamfer length, which is this length across here, at about 1,447 microns. We're getting a left length of about 1,000 microns, 1,018 microns. We're getting a right length of 1,023 microns, and we have a bunch of parameters here that are best shown with this diagram right here. This is our chamfer length right here that we're measuring. And with the 3D data, we're able to recreate the material that has been removed. So by identifying this right plane and this left plane, we can tell where those are going to intersect. So we can tell you what this right length was. So this material has been removed. We can tell you what that length was. This left length has been removed, but we can tell you what that length was as well as all these angles in between. So all these angles have been reported: the center length, this chamfer length, this left and right length. So those are all the parameters that are being shown here. And each one of these is pass-fail. So if I wanted this to be at least 1,400 or to 1,600, say, this would show up as green, just as an example. If I wanted this to be at least 15, this would be flagged as a failure, as red. And you could set that for each one of these parameters. And you can save each of these in the user settings for each individual part you're looking at.
Hey, Kramer, real quick before you go on to the rounded edge, we
Yeah.
did have a couple questions about can we measure weld geometries? And if you can
Yes.
maybe show that, and then also corrosion.
Okay. So we can take a look at a weld real quickly. I just have a welded part here. We have a weld along here. I'll take a quick measurement of with the InSpec. And just like the other measurements, I'm just going to put this up to this part and get the right focal length, and then click this button and get a surface map out of it. So here's my weld. It's my live video. Get it into focus like that. Go ahead and take a measurement.
And again, just to talk about this a little bit, we can only see the surface of the weld. We can't see anything subsurface, but people do use this to look at the weld volume, the weld height and width, and also oftentimes the three-dimensional measurement will indicate cracks, because when there's a crack, there's no surface to reflect the light, and therefore we would get a void in our measurement that you can determine.
All right. I'm going to restart this.
So, and then in terms of corrosion, maybe we won't show additional measurements because we're running out of time to get through everything. But earlier we were showing the laser marking part, and corrosion pits are essentially measured in exactly the same way. So, you bring the InSpec up to the pitting. If there's multiple pits within the field of view, you can measure it, or even if there's a large dished area, you can measure that. It will calculate each of the corrosion pit depth, area, overall corroded area, because some parts have a, say, 10% limit on the amount that can be corroded no matter what the depth is. So that also can be calculated. And we also have the ability within the software to identify a reference zone, so that if you only have a little tiny portion of a part that's uncorroded, you can use that as your reference and get accurate heights as you do measurements of various pits or other features.
I also wanted to chime in. As marketing manager, I'm always thrilled that we're able to do these webcasts, and it's important to point out that this is part of our customer support structure. Kramer is an application engineer, and part of his job is installation and training. And with the pandemic, we have been investing in this internet technology to be able to provide training and installation by remote access. And so what you're seeing is something that we will do for customers as part of support in an ongoing process.
Yeah, and of course we're anxious to get out in the field in front of folks as soon as we can, but that's just not possible right now. So yeah, here you can see the overall weld height, right?
Yep, this is a surface map of the weld itself. You can get a little more detailed about it in traces, and you can draw tracing where you want if you want to look at it. If you want the overall height of it from this side, say. You can get your peak to valley there at 464 microns. And at this specific trace, there's different things you can do with the weld.
Okay.
You can measure
And
the
then
bead
Kramer,
height.
we want to be
Yeah.
conscious of folks' time. So I think
Yes.
maybe we will pause the measurements. We can pick them up again at the end if people have questions about specific things. But I know we did have some inquiries about automation as well as CAD comparison. So maybe if you just want to show
Yeah.
people real quick.
Yeah. So this is a example of our automation. We have here mounted the InSpec on our on a UR3 robot. The UR3 robot, universal cobots, are supported natively in our software. So we have a nice interface that allows you to set up a program. So here we have we're going kind of slow to demonstrate it, but we have a program set up to measure all these defects on this particular part. So this InSpec is taking measurements at set spots on this wheel. And if you want to use your own robot, I could show you this. This is the interface we use. We can set your own program here, set your measurements, tell you to save data there, so you can make a routine, set your data, and have pass-fail criteria for each of your measurements. If you want to use your own robot, we can do that. We have a remote interface that allows you to use. If you have a different type of robot instead of a universal robot, we can also export, as we were saying earlier, 3D measurements as X by Z point clouds. If you want to do CAD comparison, and I'll go ahead and show one other video before we get into CAD comparison of the automation we have. It works for edge break as well. So here we have that this part, this automotive part. We're measuring chamfers on this particular part, and these have dozens of chamfered holes. So it's having a universal robot like this expedites the process. It can go to each of these holes and take a measurement and do its performance chamfer analysis on each one using this automated system.
Great.
And for CAD comparison, you can pull up an example of that right here. So what we did in this particular example, it was we 3D printed our own little figure, little part right here. And then we can take a 3D surface map using the InSpec of this 3D printed part right here. And we can throw our CAD model of that 3D printed part into a third-party software, and we can overlay our 3D surface map that we took with the InSpec onto that part. And using, by comparing the CAD model to the 3D surface map, we can point out basically what we're doing here is how good our printer was. So you can see here we have a little bump, the most significant bump on the print. That's where it deviates from our 3D surface map that we took with the InSpec. So we have this bump here, and the ridges are a little low, they're a little bluer. So this bump is high, and the blues are low. It's essentially how we're comparing with a CAD model. So overlaying our 3D surface map that we take with the InSpec to our CAD model, and that can be done with any type of part that fits within our field of view.
All right, great. So I think with that, maybe we'll wrap up for now. Again, we can do additional measurements during the Q&A session as necessary. But, and we do have one question actually already, which is someone was asking about the roughness parameters within the software. And I'll just comment on those briefly. So we do actually calculate both the R parameters, so RA, RQ, RT, as well as many of the S parameters, which are the three-dimensional surface parameters. However, as the system noise floor is 2.5 micrometers, there's only certain surfaces on which that will be valid. So if you have a polished metal surface or a fairly smooth metal surface, chances are the roughness is beneath our 2.5 micron noise floor. So we would not recommend actually using those parameters to make determination about your part, because you're more measuring our noise. But there are many surfaces such as 3D printed material, cast iron, textured metal, shot peened surfaces, all of which do fall within our noise floor. And so we do have quite a few customers out there, others looking at textured rubber or textured metal. Those people do actually use the surface parameters. So we offer them, but this is not really a surface finish measuring system because of that 2.5 micrometer noise floor. So with that, if there's additional questions, we're happy to answer them, or we could even do more questions if you want to, or more measurements if you want to type them in. So feel free to ask away. All right, it seems maybe we are let off the hook. You can direct additional questions to Flavio, and other than that, we thank you all very much for your time this afternoon, and let us know if we can provide additional information or arrange to have parts measured, by the InSpec for you. Thank you very much.